Welcome to this explainer. We're jumping straight into the spatial magic behind support vector machines. This is a genuinely, incredibly powerful machine learning algorithm, one that actually dates all the way back to 1963. And you know what? It still remains one of the most elegant tools in a data scientist's toolkit today. We're going to visualize exactly how this mathematical marvel works by looking at the geometry of how it actually makes decisions. To really wrap our heads around how algorithms classify complex data, we have to start with a pretty fundamental question. How do they physically separate different categories in space? Think about it. If you scattered a mix of red and blue marbles on a table and I asked you to separate them, you'd probably just draw a line down the middle, right? But how in the world do we teach a machine to find the absolute perfect line every single time? Well, that brings us to the support vector machine, or SVM. At its core, it's a supervised learning algorithm used for both classification and regression, but its primary mission is just beautifully simple. It seeks to separate data into distinct classes by finding the absolute best boundary. First introduced by Vladimir Vapnik and Alexei Chervodenkis, this algorithm doesn't guess. It uses pure spatial geometry to definitively split your information. Let's break down the spatial anatomy of how it draws that perfect line. The foundational spatial concept here is the hyperplane. Now, if we're just looking at a flat 2D graph, sure, it's just a line. But in machine learning, we're usually dealing with hundreds of dimensions, so we call it a hyperplane. This is the ultimate decision boundary. Mathematically, it's defined by a weight vector, which tells us the angle of the plane, and a bias term, which essentially shifts it into the exact perfect position. Now, the algorithm isn't looking for just any old line that separates the classes. It actively hunts for the widest possible street between them. We call this the margin. It's the empty space between the hyperplane and your closest data points. By maximizing that distance, the SVM gives us a mathematical guarantee of a clean, reliable split. And that means it's going to perform so much better when it inevitably encounters brand new data. And sitting right there on the absolute edge of that margin, those are your support vectors. They are the highly specific, critical data points anchoring that boundary. Honestly, they're so important, they literally give the algorithm its name. The coolest part is you could delete almost every other data point in your entire data set. And as long as you keep those specific support vectors, your model's boundary wouldn't move an inch. They completely dictate the hyperplane's position. But, as we all know, real-world data is rarely perfectly tidy. So let's talk about the mathematics of error and how we penalize mistakes. Dealing with messy data, outliers, overlaps, involves a brilliant two-step optimization problem. Step one is what we just talked about. The algorithm tries to push that boundary as wide as possible. But step two introduces a mathematical penalty system called hinge loss. This actively punishes any data points that cross over the boundary into the wrong territory. It's this constant, delicate balancing act between keeping the margin wide and minimizing the points on the wrong side of the line. So the linchpin here is that this balancing act is controlled by a specific setting called the regularization parameter, or just C. Think of C as the algorithm's strictness style. Turn C way up, and the algorithm becomes incredibly strict. You get a super narrow margin just to make absolutely sure no points are misclassified. Turn it down, and it relaxes. It allows a few mistakes, but in exchange, you get a much wider, healthier overall margin. But here is the ultimate curveball for any data scientist. What do we actually do when our data is jumbled together, maybe in a circle or a really complex cluster, and it simply cannot be separated by a flat, straight boundary? Well, that is the exact difference between linear and non-linear separability. With linearly separable data, a simple straight boundary works just fine. But non-linear data, which is, let's be honest, almost all real-world data, that requires a totally different approach. We can't just draw a crooked line. Instead, we literally have to fundamentally transform the input space entirely. Which brings us to bending the dimensions with the kernel trick. This is, without a doubt, the most elegant spatial twist in all of machine learning. The core insight of the kernel trick is just wild. Imagine you have red and blue dots mixed together on a flat sheet of paper, and you just can't draw a straight line between them. But what if you could morph that flat 2D paper into a 3D bowl shape? Suddenly, the red dots fall to the bottom of the bowl and the blue dots are up around the rim. Now, you can easily slide a flat piece of cardboard, your 2D hyperplane, right between them. By figuratively bending the problem into a higher dimension, clean separation becomes incredibly simple.
But here's the catch. Actually mapping every single data point into 3, 4, or 1,000 dimensions would absolutely fry your computer. The true magic of the kernel trick hinges on the word implicitly. The algorithm figures out the necessary separation using mathematical shortcuts, specifically inner dot products. It acts as if it mapped everything into high dimensions, getting the exact same result without ever explicitly spending the heavy computational resources to actually do it. It's genius.
To pull off this dimensional bending, SVMs rely on specific mathematical tools called kernels, and each one handles different types of spatial geometry. You've got the linear kernel for the straightforward stuff, the polynomial kernel for capturing curved relationships, the sigmoid kernel, which behaves a bit like a neural network, and then you have the heavy hitter. That heavy hitter is the radial basis function, or RBF kernel. It's also known as the Gaussian kernel, and it is usually the default choice for data scientists. Why? Because the math behind the RBF kernel effectively maps your features into an infinite dimensional space. I mean, it is incredibly powerful at wrapping around complex, nonlinear relationships. It essentially finds a way to cleanly separate data, no matter how impossibly tangled it looks in its original form. So, how does this theory jump into practice? Let's check out some real-world SVM applications. Because they are so incredibly flexible, these models aren't just academic concepts, they are deployed everywhere. For classification tasks, they're amazing at recognizing handwritten text, and they are widely used in biomedical to cleanly separate cancerous cells from benign ones. For regression, they are out there forecasting financial markets and predicting real estate prices. Banks even use them to detect weird outliers, essentially acting as a highly precise tripwire for credit card fraud. Still, no algorithm is a silver bullet. Let's look at the pros and cons and get a final verdict on SVMs. The strengths are absolutely massive. SVMs are incredibly robust. They thrive in high-dimensional spaces, and thanks to those support vectors we talked about, they are highly memory efficient. But the weaknesses are real. They heavily struggle with scalability. Running an SVM on massive datasets with millions of rows is computationally punishing. Also, picking the exact right kernel can be a frustrating game of trial and error. And critically, once you start using those complex nonlinear kernels, you completely lose human interpretability. The machine knows exactly why it drew the boundary, but it becomes virtually impossible for us to visualize it. Which brings me to a final thought I want to leave you with in this explainer. If algorithms like SVMs can bend our data into infinite, unseeable dimensions to find the perfect mathematical boundary, at what point do we stop needing to understand exactly where the line is, just as long as we trust it gets drawn correctly? It's a fascinating question about the future of how humans and machines collaborate. Thanks so much for diving into this spatial journey with me, and keep asking great questions.